generating function. Actually, we can, it is also possible to define a joint moment generating function of two or more random variables, just like Flow2. For example, by T1, T2, Tn, it's just defined by expectation of, for example, for discrete case, this can be calculated by yes. Sorry. Let's see here, x, all possible x. If we have, yes, okay, something here should be 1. function of modular variables. In the following, I will show you an example. Here, we see that the multivariate normal distribution can be defined as follows. For example, let Z1 to Zn be a set of independent standard normal distribution for some constant Aij. And x1 to xm is defined as follows. Then the random variable are said to be multivariate normal distribution. Why? I will show you the reason. In the previous lecture, we just have, for example, x1 equals A11 Z1 plus 1 2 Z2 and plus Z1. And x2 just equals A21 Z1 plus A22 Z2 plus. Here, ZK just follows standard normal distribution. Let's see the expectation of x1 0 0. Here is a constant, so and expectation of x2 just equal to 2. Okay. Let's find the variance. Variance of x1. The variance can be obtained by this way. A11 Z1 plus A12 Z2 plus U and A11 Z1 Okay. Here, of course, we can explain such use definition for this one, but this way is very easy. The linear property of covariance. So this just gives covariance. Here, constant does not influence our result, so here we use the result that because Z1 and Z2 are independent, here, independent standard normal distribution, that is to say, covariance Z1 and Z2 just equals 0, yes. So this gives A11 square variance of Z1 plus A22 square variance of Z2. Because the standard normal distribution is A11 square plus A1 distribution. Okay. This is for a simple case. For general case, the same idea, EXI equals mu I and the variance just equal. Let's consider the covariance of x1 and x2. Yes. Let's find moment generating function of x1. Moment generating function of x1. Expectation of Tx just equals expectation of T by A1 Z1 plus okay. Z2 just equals T expectation by because in this case Z1 and Z2 are independent. It just gives independent here. Okay. The standard normal distribution this gives expectation. Do you remember the moment generating function of exponential mu t plus sigma squared t squared? Okay. Let's review that. Okay. For general normal distribution with two parameter mu and sigma square, this is just moment generating function. So here just gives in our case standard normal distribution means mu just equals we also have gives exponential mu t. This gives exponential. In this case, 0 unit. T squared. So in our case, sigma squared equals 1. This gives 2 over A11 squared T squared. Okay, and by exponential A1 squared T squared. Okay. Then rearrange the term. This gives exponential mu1t. Yes, mu1t. This gives mu1t plus A11 squared plus A12 squared t squared. Okay, what's this? This just shows that x1 follows because there is a one-to-one correspondence between moment generating function and distribution. So this normal distribution with A11 squared plus A12. Okay, I have shown you that under such setting. Actually, x1 follows normal distribution with this parameter. The same is for x2. Okay. Okay, let's now determine the moment generating function, joint moment generating function. That is joint moment of x from x1 to xn. Okay. The first thing to note is that this one is itself a linear combination of independent random variables z1 to Zn. So it's also normally distributed. Previously, I have shown you that just linear combination of normal distribution also follows normal distribution. And this one. Also follows normal distribution, but we actually up to now we do not know these two parameters. Let's find it. To find the expectation because linear combination we can change the order. This is a parameter constant xk just equals k. Here mu k by tk. Okay? Let's find the variance. covariance. Okay, to find this one, let's use a pure simple example. Just use x1, x2. Let's find the covariance of x1 and x2. The covariance in pure simple example x1 and x2. Let's find the covariance. Substitute the definition. This gives alpha 1 z1 plus alpha 1 2 z2 plus mu 1, and this alpha 2 1 z1 plus alpha 2 2 z2 plus mu 2. Okay. Use the linear property of covariance, just gives alpha 1 1 z1 plus alpha 1 2 z2, and no constant influence here. Z1 and alpha 2 2 z2. Because Z1 and Z2 are independent, this gives alpha 1 1 alpha 2 2 covariance Z1 and Z1. Z1 and Z2 independent, diminish. So just because alpha 1 2 by alpha 2 2 covariance Z1. Just equals 1, standard normal distribution. So this gives alpha 1 1 alpha 2 2 plus 1 2 by alpha 2 2. Okay. Generally speaking, Xij covariance Xi and Xj under such setting, then the covariance just gives K equals 1 to we have n, yes. That is x I k by alpha j. Okay. For general case, variance can be obtained by linear property of covariance. So this gives this one, Ij covariance. Here we just find covariance. So if x is normal random variable with mean mu and variance sigma square, then this is just moment generating function of y. We see that this one, moment generating function t1 tm, is given by this. same as this one, but this is for multivariate distribution. So which shows that joint distribution of x1 to m is completely determined from knowledge of this one, mu I, and covariance, this one. Actually here, which is just element of covariance matrix. That shows that x, that is the reason why x1 and xm, x2 objects are known as a multivariate normal distribution. In simple case, Z1 until Zn are independent, but use their linear combination to represent xk. So in such case, x1, x2, or xi and xj are not independent. That means their covariance are not zero. This example shows you what is a multivariate normal distribution. Okay. This is the end of the discussion of moment generating function. We summarize the content we have learned in this part. In previous section, we just use the definition to find expectation and variance. We need a long procedure. But if we know the moment generating function, then it is very easy just differentiate the moment generating function with respect to t and evaluating at t equals 0, then it's very easy to find nth moment. If we have nth moment, it's very easy to obtain the expectation and variance. Okay, and in a lot of proof, for example, if x1 follows Poisson lambda 1 and x2 follows Poisson lambda 2 and x1 and x2 are independent, use moment generating function, it is very easy to prove that x1 plus x2 also follows Poisson with 2 parameter lambda 1. Okay? Such case, you use moment generating function is very easy. Okay, can you follow me? Okay. Let's move on to a new section, namely conditional probability and conditional expectation, or conditional mathematical expectation. The reason is twofold. The first, in practice, we are often interested in calculating probabilities and expectation when some partial information is available. Hence, the desired probability and expectation are conditional one. The second, if in calculating of desired probability or expectation, sometimes it is very difficult to obtain the probability or expectation directly. So, we often to first condition on some appropriate random variable, namely just integrate the partial information to our total information. Okay, in the following, I will give a definition and show you an example how to use the idea of conditional one to find the probability or expectation. Actually very powerful and very useful. Let's from the definition of conditional probability. We recall that in the previous chapter we have defined the conditional probability of event. Namely, we have two events E and F. The conditional probability of E giving F can be calculated by this one. Of course, here we need the probability of F is is greater than 0. If X and Y are discrete random variables, this one, namely conditional probability mass function, uses can be calculated by just same as conditional probability of event. This is a joint PMF. What is this? This is just a marginal PMF of Y. Okay, this is for a discrete case. For continuous case, we will consider the continuity in the following. Let's first find this is the conditional probability mass function, PF. We can find conditional cumulative distribution function. Here, just definition, here use Y as our condition, namely given Y, X, so Y. The definition is just X less than or equal to small x t, Y for discrete case, this gives xi less than equal to x, probability that x equals xi t y. This is just for a discrete case. Use such conditional probability mass function, we can find the conditional mathematical expectation. A notation is like this. For example, conditional expectation of the first. Here, small y is just giving, can be calculated by all possible value xk. Xk probability that x equals xk giving y equals y. Okay. This part here is just considered as a constant. We use this one, we can also define the conditional expectation of x given our condition is also random variable 1. This gives you such one, just gives
Hello.
use this one
Hello.
to calculate. Okay.
Hello, Prof. Hello, Prof.
Here, most important thing here, main difference, this one and this one.
Hello.
In this case, y is treated as a constant given
Hello,
condition.
Prof.
Here, y is just random variable. So we need to take all consideration about y. So here.
Hello, Prof. Good morning.
Okay. In other words, definition are exactly as before, with expectation that everything is not conditional on the event capital Y equals Y. If X is independent of Y, then conditional mass function, distribution, and expectation are the same as unconditional one. And okay, I will show you because this is very easy, so I use slide directly. This is what this is a conditional probability mass function, just by definition. If X and Y are independent, then this probability can be represented by a product form, then constant. This one equals this one. That means conditional one equals unconditional one. That means X and Y are independent. Okay? An example.
Hello, Prof.
Let's see the following example. Suppose that G of x, y is joint PMF of x and y is given by this one. Calculates the mass function of x given y equals 1. Here you just need find a table. Here, x can take, y can take. X can take 1, 2. Y also can take 1, 2. Okay, just take a break.
di topik kenapa negara itu Tolong ini cek ya. Jelas kok. Nanti
Okay, let's return. We write the joint PMM 0.5 and 0.1 2 1 0.1 and 0.6. Something wrong here? Something wrong here. Here should be 0.3 because the total sum should be 1. Our question is to find a probability mass function of X giving mass function giving y equals 1. So y equals 1, x 1 1 1 2 0 1 2. Okay. In such case, x is fixed to this one. So probability that x equals 1 giving y equals 1 is a marginal marginal x equals y equals 0.6. Yes, the marginal of 0.4. So this gives p x equals 1, y equals 1 over probability y equals 1. Just gives 0.4 over 0.6 just equals 5 over 6. Okay. Similarly, probability that x equals 2 giving y equals 1 just 1 over 6. Okay? Similarly, we can find the probability that x equals 1 giving y equals 2. Calculated directly, just equals 1 over 4. And probability that x equals 2 giving y equals 2 just equals 3 over 4. Can you follow me? This example is just for how to use the joint PMF to find the marginal line. Okay, here, and it's not use the result. The result is right. Okay. Next one. If x and y are independent Poisson random variable with the respective mean lambda 1 and lambda 2, calculate the conditional expected value of x giving some of these n. That is to calculate expectation of x, giving that x plus y equals n. Okay? To find this one. To find this one, we just need the conditional probability of x giving x plus y equals n. Okay? In our question, x follows Poisson with parameter lambda 1, and y follows Poisson with lambda 2, and x and y are independent. From this assumption, we find that x plus y follows Poisson. Just use additive property of Poisson with 2 parameter. With 1 term of lambda 1 plus 1. So this one, to find this one, probability is that x equals k giving x plus y equals n. Use the definition of conditional probability over this gives probability that x equals k. They are independent. So this just gives y equals n minus k. Over probability that new Poisson, then substitute the PMF of Poisson in here, just gives lambda 1 case power over k factorial and minus lambda 1 and n minus k factorial lambda 2 n minus k power e minus lambda 1 minus lambda 2, yes. And also Poisson lambda 1 plus lambda 2 n's power n factorial minus lambda 1 plus lambda 2. Okay. So here answer. This gives n factorial over k factorial by n minus k factorial, and k's power and n minus k power. What is this? This just equals n choice k, t k, 1 minus t, n minus k. Here t just equals lambda 1 over lambda 1. Just binomial with parameter n and lambda 1 over lambda. That to say, for Poisson distribution, giving condition that the sum of the is just n, the PMF just follows binomial. How to understand such conclusion? We just assume that if some accident occur, follows Poisson. There are two kinds of accident. Then for each of them, just like the binomial process of binomial sequence, just like flip a coin with two possible outcome, head or tail, success or failure. Okay, can you follow me? Question?
I didn't understand the last part.
Last one.
Yeah.
How to understand such?
No, I understand this derivation, but the definition.
Definition.
Yeah.
Uh,
I mean, the intuition of the.
oh, yeah. Maybe draw a figure. For example, the process that the customer enter a bookstore just follows number of customers. For in one day, the number of customers enter a bookstore follows Poisson with rate lambda 1 and lambda 2. Okay. And the male and the female that enter the bookstore just follows X. Okay? Male and female are the total number of customers in the bookstore. Poisson. So this is that, for example, in a day, there are 100 customers had entered the bookstore. That means the number of male and female, the total number is just 100. This is just fixed. This conclusion says that under such condition, the number of female or male and female that, for example, x equals, for example, 40, just follows x follows binomial here. Yes, x just follows number of female, just follows binomial 100 and with rate lambda 1 over lambda. We return to the event of how to understand the binomial. Actually, binomial is very simple. For example, if we flip a coin, we only have two possible outcomes, 1 or 0. Success or failure. Such xi, such xi just follows Bernoulli with parameter p, okay? But in this case, we have 100 customers, or male and female. Okay. So this just follows combine this result and this result, you will find that you have an intuitive understanding why, under such case, the conditional probability is just binomial. Actually, Poisson process is a very simple process. In the discussion of Poisson, I have shown you that Poisson is just a limited case of binomial. Okay. Then to find, we see that x given here just follows binomial, binomial with n, and the lambda 1 over lambda 1 by plus lambda 2. So expectation of x giving x plus y equals n, just equals np, that gives n by lambda 1 over lambda 1. Okay. Another example. Another example. If x and y are independent binomial with identical parameter np, calculates conditional mass function. This one. This case is 4.0, and our case is binomial. We recall that binomial also has the additive property, namely two identical independent binomials, the sum of them also follows binomial. That yes, that means x follows binomial np, y follows binomial np, and x and y are independent. We have follows binomial with parameter 2 np. Yes. That to say, same as before. Just substitute these results step by step. Independent, this gives n choice k, p k, 1 minus p. No. X equals k. Yes, x binomial, yes. And y equals n choice n minus k equals m. Yes, something wrong here. M. Here. M minus k. Yes. N choice m minus k. P m minus k 1 minus p n minus m minus k. This that's 2 2n twice m Tm 1 minus T 2n minus m. Then the question is how to simplify. Answer. Okay, is 2n minus m plus k. Answer. This gives 2n twice m and n twice k and n twice m minus k. For this, this one is known as a hypergeometric distribution. It arises as a distribution of the number of black balls that are chosen when a sample of m ball is randomly selected from a basket containing m white and n white and n black balls. Okay. That's to say we have a basket. We have n white ball and n black ball. We randomly select a ball from this basket and take the total. The number of balls is just m. Among them, there are k white ball and m minus k black ball. Just total 6, which is known as hypergeometry. Okay. We also have a very interesting example. See here. See here. The total number of accidents in a mine within a year just follows with parameter lambda, the number of accidents occur in a year for those points. Assume that. The probability that accident is fatal is just probability P. Let Y denotes the number of fatal accidents within a year and try to find the PMF of Y. Find the PMF of Y. Y holds which channel distribution. To find the, for example, probability Y equals K, this is just PMF, but to find this is very direct. So we combine the two events and the relation of X and Y. This just gives X just denotes total number of accidents. So okay. Just take the marginal. This can be calculated by probability that Y equals K giving X equals L by probability that X equals L. This is Poisson. What is it? We have found it before, just binomial. Okay, I will show you again. This gives in such case, what is the total number of accidents is L. Among them, we have there are K fatal accidents. And here, accident is fatal is P. Actually, this is just binomial. Binomial gives L choice K. And this is Poisson probability that pk 1 minus p L minus k. Okay, this is Poisson L factorial lambda L power minus lambda. Then how to simplify this one? Just gives alpha factorial k factorial L minus k factorial and L factorial lambda p k and then the question to how to simplify such results. This gives lambda p base power and k factorial L equals k to infinity L minus k factorial lambda 1 minus p lambda minus k and by okay. Here just equals, we just introduce a new variable, we just define I just equal defined by L minus k. Then I from 0 to infinity, I factorial lambda minus 1p I power, this just equals, this just equals lambda 1 minus. So finally, this gives P factorial lambda ps. Is power minus lambda by lambda minus lambda p just equals lambda p takes power a factorial. What is? What is? Also for assume this new parameter lambda by p. Okay. Consider experiment results one of three possible outcomes. Outcome I occurring with probability pi, a summation of p1, p2, and p3 just equals 1. Suppose that independent replications of experiment are performed, and let xi 1, 2, 3 denote the number of times outcome I appears. Determine the conditional distribution that is x2 x conditional distribution, for example x1 equals k, given that x2 equals m. Here, they are independent replication. So we see that x1 plus x2 plus x3 just equals n. So this is 1, this is m. This one should be greater than or equal to 0, so k must less than or equal to n minus n. Okay? How to find such conditional probability? This gives probability that x1 equals k and x2 equals m over probability that x2 equals m. this is probability that yes, x1 equals k and x2 equals m and x3 equals n minus m minus k. How to find this one? Actually, I just, but today, the lift time is not enough. I just give you a hint. Please consider it after the class. And here, this one should be calculated. The total number of events or outcomes is just n. We have n outcome 2 with probability p2n's power and 1 minus p1 minus 1 minus p2. Just consider reason why this relation. And this one, this gives just a multinomial distribution. What is multinomial distribution? Okay, today let's stop here. Next time we will analyze